We can further clarify the predictor-corrector process perhaps by writing everything out in columns, as we did before. We start out just as before, clock time 0, temperature 150, the rate -2 degrees per second. Not writing the units in so we can get all the information in one table and still be able to see everything. Okay, if delta t is 5 seconds, and of course -2 degrees per second for 5 seconds gives a predicted delta t of -10 degrees. Now we're just saying that's a predicted -10. We're not really going to apply that -10. We're not going to say that we go down to 140 over here, but we will say that based on this prediction, our predicted temperature would be 140, so that our predicted rate would be -1.68. Now we have two rates. We have a rate of -1.68 degrees per second and a rate of -2 degrees per second. We correct our rates by averaging these two, and we get -1.84 degrees per second, which gives us a -9.2 degree change, and we apply that back in our original column, and we say that the temperature is 140.8 at t equals 5 minutes. We could then follow this process, get our dt, our rate for 140.8 degrees, apply that for 5 minutes, use that as a predictor, predict the temperature, predict the rate, average the two rates in this column, and get a corrected delta t, which we would then apply. And we would continue the process in this manner. This predictor-corrector method is a little more work per step, but we have to take a lot fewer steps. In a step of using a delta t of 5 minutes, we actually get better accuracy than we would using a delta t of 1 minute with the original method where we didn't do the prediction and correction. And actually, it turns out that we've got to take maybe, rule of thumb, about 1/10 as many steps with a predictor-corrector method to get the same precision that we would with a straight method without using a predictor-corrector. That is, that we can use a time increment that's 10 times as long and still get good results that are as good as we would with the original.